So in this next section, we're going to learn some more applications about these exponential functions. We saw in the last one, we had that uninhibited growth, so the population can continually increase. Now we want to look at the reverse case where the population's continuously decreasing. So basically we had that differential equation before, dB dt is equal to some constant times the population. So that constant K was the percentage that that particular population was growing by. So you can think of this constant K as the birth rate minus the death rate. So a population is going to grow when the birth rate's greater than the death rate. If the reverse is true, so you're dying more than you're inputting new individuals into the population, then this constant will be less than 0, and the population is what we say is decreasing or decaying. So basically you can write the same type of differential equation, but now it's decreasing. So the rate of change is negative. You still have the same type of solution for this. So the function that satisfies this differential equation is the initial population times e to the negative kt. So this is exponential decay. Okay? So we have the two visualizations between these. This first case was the last one. Your population's continually growing. So that constant was the rate at which you're increasing by, and you have the same formula or the same function that satisfies it, which is exponential. In the case you're decaying or decreasing, then the value of k is going to be negative. So we can think of this more realistically. If you have any type of chemicals, those are going to decay over time. Carbon dating follows some of this models, and then we're going to learn about Newton's law of cooling. So if you put a hot object in a room temperature situation, it's going to eventually cool, and it satisfies an equation just like we have before. So let's look at an example. A particular chemical has a decay rate of 3.2% per year. So the rate of change of the amount N is given by this differential equation. So the rate of change of this chemical with respect to time is it's decreasing. So it's negative 3.2% of the previous amount. So we want to see a function that satisfies this equation. And since it's in that form, you get the initial amount of the chemical times e to the negative 0.032t. So you can always check it by going ahead and differentiating, just making sure that when you take the derivative, you get this extra negative 0.032 that pops out by chain rule. And then this part here is exactly the population n of t. So yes, the rate of change is negative 0.032t. So this is good. So now that we have our function that talks about the amount of chemicals over a certain time t, suppose we have 1,000 grams of this substance to begin with. So it's present at t equals 0. We want to see how much is going to be left after 60 years. So all that 1,000 is it's your initial amount, so it's n sub 0. So we need to plug in 60 into this equation. This becomes 1,000, and then we replace t by 60 because we want to see after 60 years. So if you plug this into your calculator, it's going to be about 146.6. So in 60 years, you'll have 146.6 grams remaining. Okay. Now we want to answer a similar question. We were concerned about the doubling time last time or tripling time. Now we want to see after how long will half of this original 1,000 grams remain. So what we need to do is we need to find at what time t will the total amount of the substance be half. So when will it be 500 grams? So we need to solve the equation 500 equals 1,000 e to the negative 0.03t. So you go ahead and divide by 1,000 to make those cancel. and we're left with 1/2 equals e to the negative 3.2t. So if you go ahead and you take the natural log of both sides, it's going to make the natural log and the e cancel. So natural log of 1/2 is negative 0.03t. You can break that apart just to kind of see it's going to be similar to the last one. Natural log of 1/2, because it's division, you can write as natural log of 1 minus natural log of 0. And then the natural log of 1 is just 0. So all this ends up being is we want to solve negative ln of 2 is equal to negative 0.032t. So you divide by that, and you get the time is the natural log of 2 over 0.032t. So it'll take about 21.7 years. So this is called the half-life. It's very similar to that doubling time. So what we saw before is if you wanted doubling time, you took natural log of 2, divided it by the percent or that growth rate you had. If you wanted tripling time, it was ln of 3. So if we wanted to see how long it would take to have a third of the substance, it would follow in the same way. It would be natural log of 3 divided by the rate. So in general, the half-life is going to be T equals natural log of 2 divided by K, and K is the rate that we're going to be decaying at. So if we look at a particular substance, plutonium-329 has a decay rate of 0.0028% per year. We want to figure out what is its half-life. So we take natural log of 2 and we divide it by that rate. So you have to move that decimal 2 more times. So you get an extra 0 in here. Okay. So we take natural log of 2, and I'm missing a 0 right there, and divide it by the 0.0028 as a percentage. And what you're going to see is this is about 24,755 years. So plutonium-329 has a half-life of 24,755. So it would take this long for it to lose half of its original amount. So let's look at an example that's really kind of like carbon dating. So the amount of carbon present in animal bones after T years is going to be given by this function, where that n sub 0 is the initial amount of carbon in that item. So we want to figure out how old is an ivory tusk that has lost 37% of its carbon-14. So I've lost 37% of my amount. So because of that, we've lost 37%, we still have 63% of the carbon remaining. So what we need to do is we need to find the value of T that makes it so the output is 63% of the original amount. So basically we want to see what's 63% of the original. Okay, so what we can do is we can set up an equation. So we'd have 0.63 n0 over here is equal to our function. Then we want to divide by n sub 0 to be able to solve, and that makes it all cancel. So this gives us 0.63 is e to this large exponent. Again, we can take the natural log of both sides, or rewrite this to get natural log of 0.63 is equal to this times T. And then if we divide by that, we get T is natural log of 0.63 over this. So that would make the ivory tusk 3,819 years old. Okay. So this works for any type of carbon dating. Just be careful about what the question is asking you. So we can utilize this. We learned about continuous interest last time. So we saw if your interest is compounded continuously, we had that A equals that initial amount, your principal, times e to the RT. So what we want to do now is suppose I know how much my interest is, and my goal is to get a specific amount of money. So maybe we want to invest money in an account that earns 4.1 interest compounded continuously. So that in 5 years, I'm going to have $10,000. How much am I going to have to invest into this account to make that happen? So I know that my principal is equal to my amount in my account is equal to my initial e to the kt. I want $10,000 in my account, and my goal is to figure out how much do I need to invest so that in 5 years' time, I'm going to have $10,000. So we need to solve for this initial amount. So if you multiply those exponents, that's just e to the 0.205. And if you go ahead and move the e over, you're going to get that the principal amount you have to invest is 10,000 divided by e to the 0.205. So if you plug that into your calculator, if you want $10,000 in your account in 5 years, today you would need to invest $8,146.40. Okay? So that's how much we have to invest to gain what we want in the future. So what this is called is the present value. So what is the present value I have to input to gain this in the end or after a specific time? So in general, we have this equation, P equals P0 e to the kt. If you want to solve for that present value, you just bring the e over to the other side by dividing it. But anytime you have an exponent in the bottom, you can always bring it to the top as a negative. So the present value, P0, of an amount P due t years later at an interest rate K is given by this formula. So all it is a rearrangement of that continuously compounded interest. But now I can figure out to get $10,000 in 5 years, this is how much I need to invest. So it's just really reversing those roles. Right? So let's look at an example. To save for college, after your birth, your parents want to make an initial investment that will grow to $20,000 on your 18th birthday. If the interest in the account is compounded continuously at 3.7%, how much should they invest? So basically, assume right now you're going to have a child. You want to put money in their account today so that on their 18th birthday, they have $20,000 to go to college. So I'm going to put one lump sum, it's going to grow to $20,000, and the rate I'm getting is 3.7. So we're just going to use this other formula we have for present value. P0, the amount you have to invest, is the future value. So we want $10,000. Here's our rate, 0.037, so 3.7%. And then our time is 18. So if you plug this into your calculator, this is about $10,275.19. So today, if you want $20,000 on the child's 18th birthday, you need to put in $10,275.19 to ensure that you get that money. Okay. So now the last thing we're going to talk about with these applications of decay is Newton's law of cooling. So the whole idea is if you make a cup of coffee, you make a cup of tea, or really even if you put like a ice water cup outside in the hot sun, those objects are going to change their temperature to kind of match their surroundings. So they're either going to get cooler or hotter. So in this case, we're going to look at the instance when it's cooling. So we have a temperature T of an object. Assume you've made a cup of coffee. It's going to drop at a rate proportional to kind of the difference in the temperature and its surrounding object. So your house is set to maybe 70 degrees, but as soon as you make this cup of coffee, it's 150 degrees. It drops at a rate proportional to the difference. So there's an 80-degree difference between the two. I'm going to lose my temperature of this coffee at a rate proportional to it. So the differential equation we have is the rate of change of the temperature with respect to time is going to decrease, so it's negative K, times T minus C. So that's the difference in the temperature of the actual object and the surrounding medium, so like the air. So it still has a similar form to these decays because it's got the negative K. It still has T. We just have this extra term, that minus C, that plays a little bit of a role. So you can look in your book if you want to see where this formula actually comes from, but a function that does satisfy this equation is given by the temperature is some constant times e to the negative kt plus the temperature C, which is the constant temperature of its surrounding medium, so whatever the air happens to be. So these equations can get pretty long because it's going to vary from problem to problem. You're not going to have a set value of C. You're not going to have a set K because it's all dependent upon the two things you're working with. So let's look at an example that deals with coffee. Wawa finds the temperature of its freshly brewed coffee is 130 degrees Fahrenheit. The company fears that if customers spill hot coffee on themselves, lawsuits may result. So room temperature is generally 72 degrees Fahrenheit in their stores. The coffee cools from 130 degrees Fahrenheit to 120 degrees Fahrenheit after 4.3 minutes. So if Wawa decides to serve coffee at 105 degrees Fahrenheit to be safe, we want to see how long will it take the coffee to cool. So we have a lot of information that we're going to have to utilize to be able to figure out how long should I wait until my coffee has cooled enough. So let's kind of jot down some of that key information. First thing they tell us is that when we fresh brew the coffee, so the time is 0, it starts out at 130 degrees Fahrenheit. The temperature of their stores is 72. So this constant surrounding medium is 72 degrees Fahrenheit. So we're going to use this to first find that value of A. Okay. So the formula we have for Newton's law of cooling is that the temperature is AE to the negative KT plus C. So when T is 0, you're going to plug in 0, and all that's going to do is make this e to the 0, which is nice because that's 1. The temperature at 0 is 130. And then we get e to the 0 is 1, and then the temperature of the surrounding medium is 72. Okay, so this part comes from here, and then the temperature at 0 degrees is at 0 minutes is 130. So you can just subtract 72 from both sides to get that A is 58. So really, all that A is going to be, regardless of your problem, is the difference in the original temperatures. So what's the starting temperature of the object, and then what is the temperature of its surrounding medium. So this helps us fill in our formula a little bit. I now know this value of A here. So T of T is equal to 58 e to the negative KT plus 72. The problem is I don't know this value of K yet. But I have another piece of information that we haven't used. We're told that after 4.3 minutes, the temperature is going to be 120 degrees. So the temperature at 4.3 minutes is 120 degrees. So we're going to utilize this to help us find the find this value of K. Right? So what we're going to do is we're going to plug that into a formula. So the temperature is 120 when the time is 4.3. And now the only unknown in this equation is K, so we just need to solve for it. So first thing we're gonna do is we're gonna subtract 72 from both sides. So that gives us 48 equals 58 e to the negative 4.3 times k. And then go ahead and divide by 58 to get 48 over 58 is e to the negative 4.3k. Then you can go ahead and you can take the natural log of both sides or rewrite it, but those cancel. And so we get natural log of 48 over 58 is negative 4.3k. Solving for k, you divide by the negative 4.3. So when you do that and plug it into your calculator, the value of k is about 0.044. So now we know a formula. The temperature of the object or temperature of the coffee after time t can be given by 58 e to the negative 0.044 t plus 72. So we're almost there, but our ultimate goal is we want to see how long will it take for the coffee to cool to 105 degrees Fahrenheit. So the last thing we have to do is we now can find the value of little t or time to give us an output of 105 degrees. So all we're going to do is replace this by 105 and see what value of time satisfies it. So we get our temperature formula has to equal 105. So go ahead and subtract 72. And then you get the exponential times 58 has to be 33. So divide by 58 and you get a nice expression involving e. Take the natural log again so that those cancel. And we get negative 0.044 t is the natural log of 38 over 58. And then finally, we get the exact value of t, which if you plug into your calculator is about 12.8. So it'll take about 12.8 minutes after it's first brewed to reach 105 degrees. So that tells us they should wait around 13 minutes to serve their coffee after brewing.